All righty. Well, welcome everyone. This is the Istio 0 to 60 workshop. Myself and Peter, Eitan Suez, and Peter. Yeah, how do you pronounce your last name? Yasovich?
Yeah, that's close enough.
Close enough? Okay.
Yes.
All right. Well, we're happy to be here. We've got what I think is a terrific workshop that is going to take you from 0 to 60 with Istio. So what do I mean by that? This workshop is really designed to get you up and running quickly. The focus of the workshop, of course, is Istio. And what we basically expect you to already know, the prerequisites, so to speak, is just a basic understanding of Kubernetes, Docker, and the Linux command line. And armed with that sort of set of skills, we're going to upskill you to starting your journey with Istio. All right, so what is this workshop going to be like? It's what I like to call lab-driven training, which is to say that I want to minimize the use of slides. We're not going to kill you by a PowerPoint. We're going to try to do the opposite. We're going to spend as little time as we can in a presentation mode, and we're going to give you tasks. We're going to be your taskmasters, right? We're going to tell you, here's a lab, here are some objectives, but we're going to introduce you to each lab. All of the labs together form a journey. And I think it'll give you a wonderful sort of tour of Istio from beginning to end. And something I personally like is your active participation. Just because I'm the guy with the mic here with Peter doesn't mean that you can't ask questions. We're monitoring Slack, and this whole thing is going to be hands-on. So if you get bogged down in something or you don't know how to proceed, please definitely let us know, and we'll address the matter. So it's really very much a learn by doing approach. All right, so what exactly are we going to do? This is sort of the menu. We're going to begin by introducing you to your lab environment. When you want to work with Istio, basically all you really need is a Kubernetes dial tone, right? We're going to use a bash shell as our terminal with kubectl, kubectl. And then we're going to overlay on top of it. We're going to go through the process of installing Istio and then exploring it. So the sequence that we're going to follow is we're going to make sure everybody's all set with their environments. We've already created the Kubernetes clusters for each of you. And it's just a matter of getting you access to the environment. We've set up environments in the Google Cloud, and that will give us that Kubernetes dial tone. We'll talk about Istio from a very high level, give you an introduction to what problems that Istio addresses. And then we're going to proceed to install Istio. That'll be our second lab after the first lab, which is going to be really the bootstrapping lab. And then once we have Istio, we're going to talk about sidecar injection and deploy an application to our cluster in order to have, basically our test subject is going to be this application, right? And once that application is up and running, then we can really do this whirlwind tour of many of the most important features of Istio, including observability, security, and traffic management, among other things that we'll be exploring. So that's the agenda. I hope you're excited. And I have the first link to share with you. And you'll notice this link is not just on this slide, it's also the topic to the Slack channel that is set. So you can either click on it from the Slack channel if you're already in Slack, but this is the URL, tetratelabs.github.io. And I'm going to click it and show you. And it looks something like this. So this is essentially what you're looking at here is the course materials for this workshop. And in this workshop, we're going to go through all the labs you see there in the sidebar on the left-hand side. Let's make this a little bit bigger, perhaps. It sounds like a lot of people are just in Zoom and nothing else. So we're going to ask everybody to join Slack, the Tetrate Slack. Yeah, and Peter just posted the link again there. And join it. And once you join the Slack channel, Istio 0 to 60 workshop, you'll see the link there as well. Okay. So take a minute and go ahead and do that right now. Don't worry, you won't be left behind, but please join. Super, you got it. All right. This is essentially our lab materials is what you're staring at right now. And we're going to go through these labs. The first one will be the lab environment setup, which I just alluded to earlier. So it's not a bad idea once you've got a tab open with the course materials. It should say Istio 0 to 60 labs. Go ahead and bookmark that so you can get back to it at any point in time. Even after the workshop is ended, you'll be able to access these materials. So, all right. So a couple of words about our environments before we start. We've pre-provisioned the Kubernetes cluster for each and every one of you. We've pre-provisioned a GCP project that you can join so that you can access that Kubernetes cluster. And you'll be using a feature of GCP, which I personally value, called the Google Cloud Shell, which is really a terminal built into your web browser that will give you access to all the command line tools that you'll need for the workshop. So it's all set up there for us, and we'll make ourselves right at home there in just a minute. All right, so we're going to start with a lab to get our environment set up. Maybe what we should do together is kind of peruse through what the lab is going to ask you to do, okay? And let's do that together. And then what we're going to do through the process of working through this material is this sort of overview that I'm about to give you, that I'm going to give you a little bit of time to work through the lab so you can get your environment set up. And then once we're all done, we'll do a quick review. We'll demonstrate a few things. So at a high level, you're going to be logging into GCP. Now, you don't need to create your own account. We've already created credentials for you. And Peter has even set up a link that will allow you to retrieve your credentials for that account. Okay, so that'll be the first step, is logging into GCP, and I'll demonstrate that. Then the next step is to select the Google project that has been created for you. And once that project is selected, it's like kind of like a current working directory type of thing, right? It's your selected project is what it's called. Once you've selected the project, it's just a matter of launching this Cloud Shell, and then you'll have your terminal. There's a little icon that looks like this over here, and you'll have a terminal in which you can run commands like kubectl. You'll find out that kubectl is already installed, and then it's just a matter of setting up your kubeconfig file. So we'll walk you through how to do that. And once your kubeconfig file is set up, you can access your Kubernetes cluster. The last step in this lab is just running a command, this git clone command that you see here on the screen, which is essentially going to download to your Cloud Shell a list of YAML files that you're going to be using throughout the labs. Okay. So that's, in a nutshell, what we're going to do in this lab. It's called the lab environment. And I wonder, okay, I think this is the time for us to communicate to everyone their credentials. So I think Peter is going to take care of that, and he's going to share with you a link to an app. And
Yes.
the way is, yes.
Yeah, it's already posted in the Slack channel. So if you go onto that link, you'll have to enter the email address you used to register, and then it'll give you the GCP email address and password you can use to log in. If it doesn't work for you,
yes, workshop account. Yes, that's right.
Yeah, so workshop account. It's Tetrate. Yeah, it's this website.
So this is what it looks like. So you'll click on the link and you'll enter. Yeah, this is, Peter was saying, the email address that you use to register for the workshop, and it'll give you your username and password.
Yes.
Well,
yeah. If it doesn't work, just DM me on Slack, and I'll send you the username and password you can use if it doesn't work.
Yep. All right. So while you're getting that, everybody's sort of working on getting their username and password. Let me show you what you're going to do with it. I'm going to demonstrate this. There's a link here in the lab instructions that you can just simply click on. I like to command click on it so that it opens in a separate tab. And the basic idea there is now I'm already logged in with a particular account. I'm going to switch to an account that looks a lot more similar to what your account's going to look like. It's going to have a look and feel that resembles what you see here, but your project will not be selected yet. So for those of you who've never used GCP, I'm going to give you a 2-minute quick overview of what you need to be aware of. There's a search bar here, which is useful. There's the project selector here, which is crucial, right? And then there's the hamburger menu on the left-hand side, which is very important. And then finally, there's this icon here to activate your Cloud Shell. So first things first, the first thing you're going to need to do is click on here, which will bring up a pop-up dialog, which will allow you to select the Google project that has been assigned to you. Now, before you'll be able to do that, you'll be obviously logging in with the username and password that was assigned to you. And there'll probably be a pop-up that will ask you to accept the terms or what have you. And once you're in, you'll need to select the project. Now notice there are multiple tabs here. And sometimes where it says select a project, it might actually ask you to first select an organization. And if it does, then select Tetrate Labs. And then once you do that, you click on this All tab, and you'll be able to see the project that's been assigned to you. Mine is number 24 there, and yours is going to have maybe a slightly different number. It might actually say Asia, February 2022, and with some other numbers. So you click on it, and it'll select your project, and that's all you've got to do. That'll be step one. And all of this, by the way, is described in the lab instructions in detail, okay? So once you've got your project selected, it's just a matter of turning on your terminal, the Cloud Shell. You just click on that little Activate Cloud Shell button in your upper right-hand corner of your screen, and then you'll have your shell there. And notice that it shows up in the bottom panel, and you can obviously make it taller if you need more space. I personally love to just open it in a separate window so that I can get the whole screen, so to speak. And there's a number of different knobs that you can turn, like for example, if you want to make the font size a little bit bigger or what have you, you can do that as well. All right, so this is what we want, right? Is a terminal in which we can run commands. For example, kubectl version -- client. It's just a way to verify that kubectl is already installed there. All right, the next.
Eitan, before you continue, can you just make the font size bigger?
Yes, for sure.
I'm asking for everyone else.
Yes, thank you for. Okay, I'm going to pick largest. Hopefully that's nice and big. Okay. All right. Thank you, Peter. So the next step is then to actually set up your kubeconfig file, right? So if you look at kubectl, what is it? Config get contexts. I've already gone through that step. So it's already, my kubeconfig file is already set up. Yours will not be. So how would you set up your kubeconfig file? It's rather simple. You basically click on the menu bar. You select Kubernetes engine, and you look at your clusters, and lo and behold, you should have a cluster in there. Now I'm in the wrong tab, so I'm going to try that again. I want to pick Kubernetes engine, select clusters, and there's my cluster. And basically what you do is you click on the little 3-dot menu there and click connect. When you click connect, you get this command that you can copy and directly paste into your terminal. And once you paste it in, it's basically the gcloud command to get the credentials for that Kubernetes cluster. And then you get this pop-up that asks you to authorize the request. And basically the gcloud command takes care of the rest. If you look in your .kube directory, you'll see a config file that's already set up, and you can actually run the kubectl config get context command, and your Kubernetes context will be set. And that's essentially the lab. There is really one last step here that I omitted. So that's basically running this command. So let's see what that does. And I just copy and paste this command. It's a git clone command. It clones a bunch of files in a folder called artifacts. Okay, and that folder is important because if we take a look inside, let's peek at artifacts. You're going to see there's a bunch of Kubernetes and Istio YAML files that you're going to be applying in the course of the subsequent labs. All right, so if you've done that, you're all set. So basically my expectation as your instructor is for you to go through those lab instructions, to sign on to GCP using the credentials that you obtained right here in this Istio 0 to 60 workshop form, and then select your project, turn on your Cloud Shell, and configure your kubeconfig file, and you're ready to go. And again, I'm going to remind you one more time, if you haven't already done so, go ahead and bookmark the course material URL so it's easy to get back to in case you close this window. That's always a wise thing to do.
But yeah, I think you've set up, you have your account, right? You've logged in already. I'm assuming you have the cluster set up. And then the next thing is just cloning the repo, right? Or did you already clone it? I missed it.
Yes, I did. And there's also a tip here at the bottom of the lab, which is one that I highly recommend. It gets tedious when you type kubectl over and over and over again. All right, so what I put here is a little tip that basically, if you execute this command, you can either execute this command or do it copy and paste these 3 lines, but you can add this to your bash RC. And again, I'm going to make the font size bigger so everybody can see. add this to your bash RC. All it does is, this is straight out of the Kubernetes documentation, is it aliases your kubectl command as K. That's a lot easier to type, and you're going to make less typos if you just run K instead of kubectl. I've done this, and I guess I can show you my bash RC file. And at the very bottom, you see there these 3 lines that source the kubectl bash completion. I think that's already sourced, but then the next couple of lines, alias K as kubectl, and make sure to apply the command completion to K. So I can do K get NS, and that's a lot easier to type than kubectl get NS, for example. And here I can actually see the namespaces for my Kubernetes clusters. I can also look at my nodes. So my cluster is ready and waiting for my next instructions. All right. So that's the environment bit. And that's really more of a prerequisite, something that we've got to do to get going. All right. And so what I want to do next is give you that high level overview of Istio. Right, so I see a question, where can I get the GCP credentials? There is a link that Peter posted, both on Zoom chat and Slack, with a URL to, it's called tetrate.io/workshop account. Right, and if you click on that link, you'll be able to enter the email address you used to register for the workshop, and it will return you a username and password. And if that doesn't work,
I just posted the link again to.
Okay, perfect. Yeah. Okay, so you're on top of it. I don't need to address those. All right, thanks, Peter. All right, so let's get into Istio. Meet Istio. This is, I think, the perfect introduction in that it talks about the types of problems that Istio addresses. Okay, so it's very much from a problem perspective, and I think that's really what we want to know. That gives us, answers the question, what is the reason for existence of this thing, right? Now, what is the problem statement? Here it is, the IT shift to a modern distributed architecture has left enterprises unable to monitor, connect, manage, and secure their services in a consistent way. So let's think about what that means, right? Think about this wasn't that long ago, and maybe many organizations still run many monoliths, where we had these large applications that had, as a consequence, many problems when it came to making those applications cloud native, in terms of being able to scale them horizontally, in terms of being able to run them at cloud scale, so to speak. And so we moved from monoliths to microservices. And in the context of doing that, many of the tools that were designed for monoliths, for example, in profiling tools, monitoring tools of a decade ago, were no longer applicable. And so it sort of puts us in a new world where we need to build new tools to support our ability to run and manage and secure our applications. And it's really been a big problem. And so, what has been this IT shift to a modern architecture? These are some data points, right? The move to container-based services, Docker. The fact that we deploy apps today to very dynamic environments. Things are not nearly, back in the day, everything was static. Everything had an IP address that people even could memorize, or a well-known name, or what have you. Whereas a cloud-native application is, could be dynamically scaled. You have more instances with new IP addresses that they're just new endpoints that come up and come and go. And the fact that you're running microservices basically means, that unlike a monolith where you have method calls that are all in process, here you have services calling each other over a network. So they are, what we call an application today is actually an assembly of multiple collaborating services. So our services are composed by the network. And in this sort of world, we run into the following problems. So from the point of view of monitoring, how can we monitor our applications? We're no longer monitoring one thing, we're monitoring many things. How do we coalesce logs from multiple services? How do we look at, in the days of yore, we had a stack trace that was all in process that helped a developer really diagnose and debug problems and those stack traces become fragmented as we move to microservices, as an example. We need to collect metrics from multiple services. How do we get a coherent view of what's going on in our system? That's become a major challenge that Istio addresses. All right, from the point of view of living in a microservices world, the most fundamental problem in my mind is the problem of service discovery, right? Services are available. How do you know how to reach them, right? For one thing, there's not one, there's multiple, right? They scale dynamically again, they may be upgraded or what have you. And so you need some kind of service discovery in there. And there are many implementations of service discovery. I remember back in the day looking at, I think Netflix was one of had an open source service discovery product called Eureka. You know, if you're going to work in the world where you have lots and lots of services, you need service discovery. And along with that, you need load balancing and resiliency. So as the moment you start scaling horizontally, you've got multiple endpoints that you need to load balance across. And that's for every single service in your distributed system. And then, you know, how many times, for example, as a developer, have you had to sort of hard code in your application things like retry logic or, you know, timeouts, customized timeouts, and then you have essentially a heterogeneous way of implementation of these rules that are littered across your sort of application landscape. And so Istio brings a lot of sanity back to this process. All right. Another problem is managing the flow of requests, and not just at the fourth layer of the OSI stack, but also at layer 7. Use things like host names, headers, request paths to basically determine how a request should be routed. There's a number of sort of cross-cutting concerns that you know, the interception of requests to check if a user is authenticated, rate limiting. There's a whole bunch of policies that need to be applied in order for the system to really be working correctly and to be also in many ways protected, which leads us to security, right? So security becomes more and more complex when you have a distributed system, and Istio brings a great deal of sanity there, and it works at 2 layers, right? The security with Istio works both at the workload layer. It essentially provides a mechanism for workloads to have their own identity. And so it allows you to actually define a policy that could say, okay, service A can call service B, but, you know, another service that is really completely unrelated to the system shouldn't be allowed to call it. You can define these kinds of policies. You can authenticate both users and workloads, and it addresses both authentication and authorization. All right. So what's the idea of a service mesh? There's a number of ways to think about this, but it's almost like a separate player when you think about it. You've got all of these applications and services, and you have to deploy them somewhere, right? We used to deploy them on VMs. Today, maybe we've already migrated to Kubernetes. Maybe we're in the process of migrating to Kubernetes. Istio takes this to a completely other level. This idea of a mesh is this sort of intelligent substrate that you drop your services into. I want to sort of paint this image in your mind. And this substrate is actually able to provide a lot of these solutions to these problems we just described, a lot of these cross-cutting concerns to the applications without the applications really needing to concern themselves with those things. So retry logic, load balancing, the ability to discover other services is all done for you in a sort of cross-cutting way. So, you know, that's a term we've used for decades, but it's actually re-implemented and it's a very elegant design. So, I mean, many of you, I'm sure, have come across or talked about or used AOP, aspect-oriented programming. They were all different ways of sort of solving the same problem. But here we see a problem solved at a completely different level that is very elegant. I keep using that term because you do not need to instrument your applications to actually be able to derive these benefits, because the mesh itself is actually external to the applications. We'll get more into what that means as we work through the labs. All right, so we've got a service mesh. Here's a definition for Istio. Istio is a platform that can let you monitor, secure, connect, and manage services in a very consistent way across your entire set of microservices. All right, and with that said, it's high time we do something hands-on, right? And here comes our second lab. So we've got access to an environment. Right, we've just talked about this environment lab, and we're going to go on and move to the next lab, which is called installing Istio, right? I mean, that's again a prerequisite. If we're going to play with Istio, the first step is installing it. And so this lab is going to walk you through it, and it's going to be a piece of cake. There's really not much you need to do. And then let me walk you through the instructions. So, and I think the folks who build Istio have really streamlined this process. I can't imagine it being any simpler. The first step is basically using the curl command to download Istio from istio.io. You can notice we're going to use version 112.2, which is a pretty recent version. I think a few days ago, a new version came out, but for all practical purposes, of this workshop, it's all going to work the same way. Once you download this thing, it already unpacks it for you. You're going to have a directory in your terminal called Istio 112.2. And that's the Istio distribution. And it's really a two-step process. So step one is installing the Istio CLI. And just like kubectl, we have an istioctl, right? istioctl, however you like to pronounce it. And istioctl is bundled in what you just downloaded. So it's just a matter of copying the binary to your path. Now, there's a little bit of a catch here, and I'm going to ask you to install the binary to a path that's in your home directory. And that's because the Google Cloud Shell guarantees the preservation of any files that you keep in your home directory, but not so for anything outside your home directory. So we're going to ask you to create your own home directory, to copy the istioctl binary there, and then to add the home bin directory to your path. And we give you the snippet here. You can it even puts it in your bashrc file, so you won't have to do it every time you instantiate a session. God forbid, that would be painful. All right. The command to verify that istioctl is installed, obviously, is istioctl version. So you can run that command afterwards and see that it's actually installed. Now, that's just the CLI. Your Kubernetes cluster has yet to have Istio installed in it. And that'll be the next step. And it's just a simple command. Now, there's variations on this command. There are multiple different profiles of Istio that bring in different components. But again, for this workshop, all you need to do is type istioctl install. And it's just a matter of replying yes to a prompt, and you're done, basically. So maybe let's do this together, and then I'll give you a few minutes to sort of work through this as well. So I'm going to go ahead and copy that first link, and I'm going to come back here to my terminal. By the way, you should know that these Google Cloud Shells have a session timeout. So if they do timeout, you'll typically see a reconnect button at the top in the header that you can just click on to reconnect. All right, so what do I need to do? Run that curl command. So here we go. We're running the curl command to download Istio. And so what I like to do is do a directory listing and verify that I've got this new folder there, Istio 112.2. Okay, great. So we step into it. And now there's a bunch of stuff in here, but all we need right now is the contents of that bin directory have the little istioctl command. And what we want to do is create a bin folder in my home directory and to copy essentially this CLI to that folder. Okay. So at this point, I don't need to be technically inside Istio 112.2 anymore. I can go back to my home directory and I can verify that I've got a bin folder with istioctl in it. That looks all good. And then the final step is essentially adding it to my path. And so you can just copy and paste this command if you like. I'm going to go ahead and do that. And then just do that. And all this does essentially is add a line to the bottom of your bashrc file. It appends it. That puts home bin in your path. Let's check. Let's go into bashrc and we should see, yeah, export path equals home bin path. And the other thing it does that we should do afterwards, since we've edited our bashrc, we actually haven't applied our bashrc file. We should source the file. So sourcing our bashrc file will make sure that that environment variable is updated. So let's run source bashrc. How do we check? We should be able to see our path, and somewhere in that path should be our home bin directory. It's put in front. So it's the first item in our path is our home bin directory. We can type istioctl version, and now it should work, right? So that's also a way to verify. So notice that the version states 112.2, that's what we want, but that our Kubernetes cluster is not yet got Istio installed. So that's the next step. So here we go. Here's the Istio install command. It's really pretty straightforward. Istio cuddle install. You'll get prompted. Yes, am I going to be installing Istio core? Absolutely. Let's go ahead and enter yes and press enter. And this process takes about 30 seconds, I'd say, in my experience. You can see that there are two components of Istio that gets installed, Istio D and Istio Ingress Gateway. And we'll explore both of them in just a minute. All right. Once Istio is installed, how do we verify? There's a couple of things you can check. One is there are a number of CRDs that get installed as well. So you can look at your CRDs, your API resources. Another one is you can look at your namespaces. kubectl get NS. And here, notice there's a new namespace that wasn't there before. It's called Istio system. This is where the Istio components get installed. So if we look at the pods in Istio system, we'll see two pods. One is Istio D, that's the core of Istio, and the other one is the Istio Ingress Gateway, which is going to allow us to handle all kinds of ingress needs to expose applications to the wider internet. And along with that Ingress Gateway, there's also a load balancer. We'll see that in just a minute. Okay, so let's see if the lab asks us to do anything else. We looked in the Istio system namespace for pods. I suppose you could tail the logs if you want. You can rerun Istio cuddle version, and you'll notice that the version now gives you more information. It actually shows you that not only is the client version installed, but what Istio calls the control plane and data plane are present as well. And that's the subject of our next presentation. So if you've gotten that far, you've got Istio installed. And then we're sort of ready to go to the next step. You may be itching to go to the next lab, but before you do that, I've got a short presentation to go through. Now, as a reminder, if you're asking yourself, well, how long is Eitan going to be talking? I need a break. We're about an hour into our workshop, and I plan to actually take a break in about 18 minutes at the here the local time will be 10:30. I think in the India time will be, what will it be? It'll be, oh no, we're not. We're only 45 minutes into it. Yeah, that's right. So we've got plenty of time.
Eitan, one tip, never do public math. That's one tip.
yeah, that's a wise
unless
advice.
You have a calculator somewhere.
Yeah. Okay. So we're now at an hour, and actually, I'm getting ahead of myself. We've got plenty of time, and so hopefully you're still with us. And I think we'll let's see. I'm not gonna try to do math. I'll heed Peter's advice, but he's gonna keep track of time for me, and he's gonna call a 15-minute break when the time comes. So good. I think. I know that some of you may actually still be working on labs, but these two first steps are really pretty straightforward. I mean, all we've done is get access to a cloud shell and connected to our Kubernetes cluster, and finally installed Istio, and we haven't really done anything. So it's high time we talk about what the next step is and how this all works, right? So we talked about the problem statement. Let's look at the architecture of Istio. And we begin with this picture, which is, you might say, the simplest possible building block for a distributed system from which we build distributed systems, right? Larger and more complicated things with more and more services, right? And so here the scenario, of course, is two services, A and B, and A is making a call to service B, right? A is initiating the call, so to speak. Now, when we do this in Kubernetes, right, we deploy each of them. We probably have a Kubernetes deployment for each. We probably have an accompanying, at least a cluster IP type service in there that allows us to scale both A and B and still have kind of a single cluster IP service IP address to reach. Now, the way this works with Istio is rather interesting. is, we call this the injection of a sidecar. So the concept of the sidecar is probably quite familiar to most of us. It's this idea that rather than build some adjunct capability directly in process into our application through third-party dependency maybe, or something of that sort, that instead we do it out of process. And we call it a sidecar. So it's a good metaphor, right? It's basically something that's outside your main vehicle, so to speak, and but you can delegate to it work. And in this case, what Istio relies on, essentially the workhorse of Istio, or the muscle, I like to make the analogy to a muscle and a brain. The muscle is Envoy or Envoy. And Envoy is a proxy, very much like many other proxies out there, like Nginx or HA proxy, or there are plenty of others out there. But Envoy really has established itself. It sort of came out around the same time that Istio was being developed, and it was sort of a match made in heaven. And so Envoy is actually deployed as a sidecar alongside each and every service. Okay. Now, what exactly Envoy is going to do is essentially the subject of this conversation. So the first thing is we deploy an Envoy with every service, and the other player, of course, is Istio-D. We just saw it; it's running in the Istio system namespace, and I like to think of Istio-D as the brain of the operation, right? And the story actually begins even before these services come onto the scene, because when they're deployed, Istio-D is there and it's listening and it's watching, right? And so it knows all of the services that have been deployed. And so it can actually communicate to these envoys and tell them, hey, service A, envoy, sidecar, you should know that there's another service out there called B, right? And so there's a component in Istio called Galley that essentially processes this configuration and sort of passes it on to Pilot. Pilot distributes configuration. So a proxy by itself, as you well know, won't be able to do anything until you configure it. And so it's Istio that configures Envoy. And this process of communicating a configuration to Envoy by pushing it to Envoy is rather interesting. There's two things I want to say about it. The first one is the fact that envoys have that capability. There are many other proxies out there that you configure statically through configuration file. With Envoy, there's actually an API, so you can push configuration to it. That configuration contains information about the various services that exist in your mesh. And now your Envoy becomes smart. It actually knows. That is when it's armed with the information to be able to say, for example, load balance requests across multiple instances of B, and it knows where to find them. It knows where their endpoints are. That's all somehow been communicated to each of these envoys. Now, there are other components in Istio. There's this notion of a policy that has to do with authorization. So that allows these sidecars to be even smarter. Now they know, for example, who's allowed to talk to them, right? So that gets distributed to each of the envoys. And then on top of all that, there's another component of Istio called Citadel that essentially has the capability of producing identities for every single workload that's running in our mesh. And so these identities are essentially what they're called SPIFFE identities, which are a combination of the NX509 certificate and a convention for naming each workload based on the service account of each deployment. Okay, so imagine now you've got not just service A and B, but these sidecars that are fully configured. They know about everything in the mesh, and they can do the bidding of our applications, actually without our applications knowing anything about it. And then behind the scenes, we've got this Istio, and the Istio part is called the control plane, whereas where our applications run, that's called the data plane. All right, so let's follow a call. This is one last piece of information that's crucial that I have yet to explain, is when A attempts to call B, what actually happened? We didn't just inject a sidecar. We actually also configured a policy inside each and every pod whereby, and it's done through IP tables, okay, whereby every single request in and out of every container has to go through Envoy. It has to be processed through Envoy. which basically means that Envoy takes over all of the networking burden and the load balancing burden and the retry burden. You can already imagine how it's able to do all the things we were just talking about a moment ago. And so you have a request intercepted by the Envoy inside A. And because it's configured, it knows where to find B. There may be one or multiple endpoints, in which case some kind of load balancing will be employed to select which instance of B you're going to use. And that's all, by the way, configurable. You can specify which load balancing policy you want. And that's where it gets really interesting, right? Through CRDs, you can communicate to Istio. You can say, this is the load balancing policy I want. And that gets pushed to the envoys. So imagine a request is being sent to B. And because all of these workloads have identities, A knows that it's talking to B. It's not talking to an imposter, for example, and B can actually know that A is calling it because all of these requests are done through mutual TLS. They're not just encrypted, but the identities of the sender and the receiver are sort of exchanged between A and B. And then the policy is checked. So the B sidecar is checking its policy, say, hey, is A allowed to call me? And if it is, then the match is made. Well, the match made in heaven, I guess. And once we let that request in, it finally makes its way to B. And then B does its thing, it does its processing, sends a response, and then A receives that response. But it all goes through that Envoy path. So Envoy is able to do a lot of things here, like upgrade the connection, use HTTP2, use mutual TLS, and you can configure exactly how you want that to work. So in summary, this is, I think, a good diagram that summarizes what we just talked about. You've got services, you've got some kind of communication protocol that's established between the envoys, and you've got Envoy actually intercepting all requests in and out of these pods, of these containers. And then you've got the brain behind the scenes, which is Istio-D, which is assigning TLS certificates to the envoy so they can do mutual TLS. It's sending configuration dynamically to the envoys every time the topology of our mesh changes, so that the envoys are aware of all the services. So imagine a situation where you scale the deployment from 3 instances to 10 instances. Those 7 extra endpoints suddenly are communicated to all of the envoys, so they know that they're there and they can send traffic to them. All right. Okay, well, that's plenty of talking. Time to get back to some kind of hands-on activity. So let's talk about the next step, right? We've got Istio. So what? We've got to have some kind of application in which to have a subject to utilize Istio. And so that's the next lab. So if I click on this next button here to the application, again, I want to give you a rundown of what you're going to do in this lab. Again, this lab is, I'm trying to feed things to you sort of in small bites. I hope you appreciate it. So hopefully I'm not losing anybody. Okay, hold on. Before I continue, let me see. There's a question in chat. Istio-D is a combination of multiple containers. No, actually, that's a good question. So let me finish reading the question and then I'll address it. And what about Envoy? How many containers are part of it? Okay, so there's some history there. Istio-D didn't used to be a single container. Today, it is a single container. It used to be sort of a set of microservices that were loosely coupled, but for the sake of being pragmatic and reducing the operational burden, today, the latest version of Istio bundles all of those components that used to be separate things like Galley and Citadel and Pilot, all into a single pod. So you've got everything running in a single pod. Now, what about Envoy? Envoy is a sidecar and it's a single container. And it's we'll see it in just a minute. Once we start deploying things, we can do a kubectl describe on that pod and see how many containers we really have. But there's basically the containers that you bring to the table, which is your application, and then there's the one Envoy sidecar per service that you deploy. Okay. Okay. So this is a question that's very apropos because it's just one thing to answer the question in the abstract, but it's another one to actually see it with our own eyes. All right, so we've got to have a sample application. And I want to bring to your attention the fact that the canonical and I see a typo there. The canonical application for Istio is the book info application. So anyone who's done the Istio quick start is familiar with book info. It's a set of microservices you can deploy to your mesh. In this workshop, we simplified things even further. We just removed a couple of players, and we have only 2 services. It's basically an application that lists customers. It's got a web front end. That's one container, one deployment. And then it's got a collaborating service that supplies a list of customers. So we've got 2 deployments that we're going to be working with, and that's what you're going to be deploying. So if you recall, let me step over to my Cloud Shell real quick. In the first lab that you did just a few minutes ago, or one of the environment lab, the last step was downloading a bunch of artifacts. So it's inside that artifacts folder that you will find the YAML files that are being referenced in this particular lab. Okay, I wanted just to point that out. So in this case, we should see some kind of application called customers and one called web front end. Let's see if we can locate them. So there's a bunch of stuff in here, I know, but there's customers.yaml, and there should be a web front end.yaml in there as well. And the lab instructions will give you their names as well. All right, so the YAMLs are there. That is, you don't have to build this app. You don't have to package it into a Docker container. That's all been done for you. You don't even have to publish it to a Docker registry. That's all done. But before we can actually kubectl apply these applications, we've got to take care of having a mechanism for Istio to inject sidecars. And there's a couple of ways that Istio lets you do it. There's an Istio ctl command called kubeinject, which will take as input a YAML file that describes just your containers and in your deployments, and then it'll spit out a modified YAML file that contains the Envoy sidecar. But by far the preferable or the easiest way to go about it is by using what's called automatic injection, automatic sidecar injection. And it's done through convention. We label a namespace. And in this case, by the way, we're going to deploy everything to the default namespace. We're going to keep things simple. And if we label this namespace with this special label called Istio injection equals enabled, what we're actually doing is we're sort of cluing Istio onto being able to inject the sidecar. And the way this works, it's done through there's a specific concept in Kubernetes called a mutating webhook admission controller, and you can read all about it if you're really curious. This is the Kubernetes documentation that talks about it. But basically, in a nutshell, what it does is it's notified every time you try to deploy something, and it has the ability to modify what you're deploying so that it can actually add the sidecar onto it. That's how that works. So you're going to label a namespace, and then we're going to check that we didn't make a mistake, that the namespace is indeed labeled. And then we're going to grab these YAMLs, and they're already in your artifacts folder, so you don't have to copy and paste them. They should already be there. But if you want to look at them, there they are. You won't find in there anything outlandish, right? It's just, what do we have here? Service account definition, a deployment that deploys. We have a spec that with a pod template specification that specifies the web front-end container to fetch from the Google Container Registry, and we have a cluster IP service fronting that. And the customer's YAML file is very similar. It follows the same pattern, so to speak, right? It's just another deployment of another image, separate pod, and an accompanying service. So once we've got the injection taken care of, when we apply these YAML files, we'll end up with sidecars. So let's test it. Let's put that to the test, right? We've got Istio installed. We've got the default namespace. There's nothing in the default namespace right now. If I do a kget pod, you'll see no resources found in the default namespace. And we're going to label the namespace default with Istio injection equals enabled. That's the magic incantation. Now, this is a useful Kubernetes command. If we do a kubectl get ns-l Istio injection, that's basically a very convenient command that takes a label and turns it into a table column, right? So you can actually see which of these namespaces has actually got that label applied to it. Okay, I see your questions. Yeah, there's an introduction of extensibility features, WASM, that also adds a great deal of functionality. Yes, that's absolutely correct. Okay, so we've got our namespace labeled. And so let's see this mutating webhook in action, right? If I do a kubectl apply -f artifacts customers.yaml, that's one of the two YAML files I need to apply. So notice it tells me that a service account, a deployment, and a service were created. But if I look at my pods, notice not only is the pod starting to initialize, maybe the image is being downloaded from the Google Container Registry, but the ready column is telling, right? It's actually saying that my deployment has 2 containers, right? And if I do the same thing again with the other artifact called web-frontend.yaml, it also will have 2 containers. And so what's that second container? It's actually Envoy. And we can actually see it. We could do a kubectl describe pod, and we can pick on one of those 2. Let's pick on the customer's pod. And now I know that's going to output a bunch of stuff. Maybe I'll pipe it through less or what have you. But there's a concept of an init container, and that's essentially a task that runs before the containers get started that ensures that all the IP table rules get put in place to route all the traffic through Envoy. But where it gets interesting is under the list of containers, you have the container itself of the application. And then you have another one whose name is always Istio proxy, and that's your Envoy. Okay, and here you can actually see the image ID and the image URL for Envoy, and with a lot of details in terms of environment variables that it's been configured with or what have you. And that's all done for us through this mutating webhook. All right, so that's all it took. The thing is running. How do we test that it's actually working? I mean, we haven't actually exposed this application through an ingress controller yet. That's the subject of the next lab. So for now, we can do a sort of a poor man's test, which is to test that our applications are functioning from inside the Kubernetes cluster. From another pod. So we need a third pod, and it's very convenient that Istio actually gives us in their samples a pod that has curl built in to the image that it deploys, and it allows us to easily make calls onto to other services, and that deployment is called sleep, and you'll find it in your artifacts folder. So if we look at the sleep.yaml file in the artifacts folder, and this is taken straight out of the Istio docs. All it is you see there on line 55 that the image is the curl image, and all it does is sleep forever, which basically means it's going to stay resident. It's not going to. It could have been an HTTP server too. That's another way to keep it resident. But the important thing is that it's 2 things: is that it stays resident, and that it's got curl installed on it. So if we deploy this kapply-f artifact sleep.yaml, we've got our sort of client container, right? And we can use kubectl exec then to make a call from inside that container. So the incantation is given to you in the lab instructions, right? Here we deploy a sleep pod, and then we do a kubectl exec, and we can curl one of the other apps. So let's do that together. We could do a kubectl exec onto the sleep pod with the command curl. Maybe we'll do customers.default.service. I'll use a fully qualified name, .cluster.local, right? kubedns. Right. So what am I seeing here? Basically, I'm discovering that all the customers app really is an endpoint that returns a list of customers in JSON format. And if I were to do the same thing, kexec from the sleep pod, a curl command to the web front end. Maybe I'll pipe that through head because I don't want to see all the HTML. You can see it's returning HTML. And basically the way it works is when you call it, it turns around and calls the customer's service and gets back the JSON, parses the JSON, and produces an HTML page. If I maybe show you all of the HTML, you'll actually see the customers show up in an HTML table in the HTML response. So that's essentially the application of the test. So That's all there is to the lab, just deploying this simple application and verifying that the application is functioning as expected. Now, what I want you to do, if you get to this point, right, is again, go back through what we just talked about in the presentation. How does this actually work, right? Remember, each one of these applications has a sidecar, including the sleep container. So when we did a curl, even the call that curl made went through its sidecar, which is an Envoy, and Envoy knew how to route the request to the customer's endpoint or the web front end endpoint. And it augmented the connection. It actually uses mutual TLS by default. There's a whole bunch of other things going on in there that we're going to discover together in the upcoming labs. All right, so that's the application lab. Let's see, I'm going to go through here and make sure that I didn't overlook anything. This might be worth talking about. This is a nice little sort of mechanism whereby you know that when you deploy any sort of deployment in Kubernetes, your pods names are derived from the deployment name, but they have a suffix that's kind of randomly generated. And so you can actually grab the actual name of your pod through this inner command here, where we can actually use the JSON path output to actually grab the name from the metadata section of the pod and assign it to a variable. And then we can, and that's a pattern you'll see in the labs over and over again. That's kind of makes it nice and easy. All right, I'm going to segue from the demo of this lab to just checking on Slack to see how everybody's doing. Okay, I don't see too many questions on Slack, although there's a lot of conversation on the chat in Zoom, which Peter is addressing. Wonderful. All right. Well, let's carry on. So let's just take stock of where we are and what we've got. We've got a Kubernetes cluster. We've deployed Istio to it. We used Istio Cuddle CLI to actually deploy Istio to that Kubernetes cluster. And then we've now deployed an application, but that application is not exposed to the wider internet. And that's really the subject of the next lab, which is how do you configure ingress with Istio? Before we go there, I think I've got a few slides that sort of discuss ingress. Ingress is kind of an interesting story from Kubernetes standpoint. It feels like there's been a number of attempts. There's the load balancer type service, which really didn't prove to be too scalable. There's the ingress specification, the CRD, which and a number of implementations, and that's also a work in progress as a gateway API spec that's being developed. But let's look at a couple of pictures here that are just going to orient us to the task, right? With that service you see on the right-hand side is it might be our web front-end application, right? It would be nice to set up something just like this, where a request from the outside, if we have in this case we have a DNS record set that points to a load balancer. We're going to actually check if that load balancer already exists, what that Envoy box is. It's actually already there. We just don't know it, but it needs to be configured. Okay, and that's really the subject of this next lab. Is you're going to have to configure your ingress to route requests to your web front end, and probably not to your customer's backend, right? Because that's not customer facing. Now, what's interesting in Istio is that your ingress controller is actually just nothing but another instance of Envoy. Envoy is very, again, versatile by definition. It's a proxy that can be configured to load balance requests, route requests, and it's just as capable of doing that at the edge as it is doing it as a sidecar. So essentially, Envoy is sort of everywhere. So that's the sort of high-level picture, and we have yet to sort of show you how that translates on the ground, so to speak. We'll see that in a minute. What's interesting about the way we configure ingress is we do it in two steps. We're going to specify exactly what host name we want to answer to and what ports we want to be able to open a connection on, and whether we want to terminate TLS or whether we want to just support plain text HTTP requests. So there's a number of ways of configuring that ingress. But once you've done that, there's a separate mechanism to actually specify, well, how should that request be routed? So that those two are separated. And I think that's an elegant design, in my opinion. There are two separate concerns, and so they're done separately. One is done through a custom resource definition called a gateway resource. And the other one is the routing concern, and other sort of traffic management related concerns will be found in a separate CRD called a virtual service. And the actual ingress controller is running in the Istio system namespace. So let's put this all together and just do a little exploration, and then I'll let you guys go through the lab and actually turn on ingress. So we need to begin by poking a little bit and looking around. So where are we going to start? Let's start with the namespaces, and let's look at the pods in Istio system. Now we see two things there. So we know Istio-D. The other one is our ingress gateway. It's an instance of Envoy. And we can even look at the labels. I know this will be a little bit busy, but the one thing that you might take away from this output is this app equals Istio ingress gateway label that's applied to the Istio ingress gateway pod. Okay, now if you look at the services in Istio system, you'll see that just like any ingress controller for Kubernetes, you have a load balancer type resource, which means that in the particular cloud we're using, in this case, we're in GCP, we have a GCP load balancer is already there, and it already has an external IP address. So that's the IP address right there. We can actually copy it and try to hit that IP address, and the answer we're going to get is connection refused, right? And that's stands to reason that that's what we want, right? We haven't configured our gateway. We shouldn't allow any requests in until we do so. All right, so we've got an IP address. Now we can grab that IP address, and that's important. So we can do it programmatically with this command. And let me just sort of break it down for you. What we're doing here is we're saying, show me the services in Istio system, specifically the one called Istio Ingress Gateway, and grab out of the YAML, or the JSON rather, the ingress IP address. And the ingress 0 IP is the external IP address. So if we just copy that, and just paste it in here, and now we have a variable called gateway IP that contains our IP address, and that's rather convenient. Now I'm going to go a step further, and I don't want to have to do this over and over again in case, you know, if my session gets disconnected and I have to reconnect it, I don't want to have to fish this command out of there again. So what I'm going to do is make a small investment, which is I'm going to put this command directly in my bash RC file, and by doing that I can guarantee that, let's test it. If I open another terminal, so there's a little plus button in Google where you can just open another terminal, and you can just echo the gateway IP environment variable. And if it's set, you know you've actually done it right. So so great. So we've got the gateway IP address sort of tucked away in an environment variable called gateway IP. That's the public IP address for the ingress gateway. But it's high time we configure it. And so let's look at these two custom resources. The first one I mentioned is called gateway. Now we're not going to do anything fancy in this lab in terms of, you know, parceling out a domain name and create a DNS record. It's not so much work, but that's besides the point. That won't teach you anything about Istio. So what we're going to do is we're just going to go with that public IP address for the purposes of this workshop. And so when you define a gateway spec, you give it a name, and you define a selector. And the selector is actually a label that is already applied on our ingress gateway. So that's the name of the selector for the default ingress gateway. And that sort of alludes to the fact that maybe you can have multiple ingress gateways, which there are use cases or scenarios that call for that. This gateway is going to listen on port 80 using the HTTP protocol. And if we wanted to change that, there's other configuration we could put in there. Now the hosts is rather useful, right? You can imagine a single load balancer that can handle multiple fully qualified domain names, maybe example.com and maybe examples subsidiary.com or what have you. And they can both go through the same gateway, but be discriminated by the host name that you associate with this concept of this gateway kind in Kubernetes. But since we're going to just be using the IP address, we're just going to use an asterisk, which basically means whatever the host name is, even if it's an IP address, just go ahead and listen on port 80 and configure the HTTP protocol. That's what we're doing. So we need to apply that. Okay, yeah, we're getting close to halfway through. So maybe once I finish going through this example, we'll take a little break. That's not a bad suggestion. All right, so let's carry on. Let's apply this gateway YAML and see what it does. Okay, so again, look in your artifacts folder, and there should be an artifact called gateway. You can look at it more closely if you like. You can look at the gateway YAML. It's exactly the same as the lab shows you. And if you do a kubectl apply -f artifacts gateway YAML, we'll get some notification that a new Kubernetes resource has been created. If you want to look at that resource, you could do a kubectl get gateways. It's just that simple. You can describe the gateway. If you want to look at the YAML, you can get with OYAML if you want to look at YAML format, what have you. All right, so the gateway has been created. And if I now try to access that IP address, notice that the response has changed. It's no longer connection refused. It's 404, not found. Why is it a 404? Because my gateway is not configured, but the route hasn't been configured. So that's the next step, is configuring the route. And to configure the route, we've got something called a virtual service. So let's take a look at that. So there's an artifact called web frontend virtual service. And here it is. It has a name. We're going to call it web frontend. The kind is virtual service. And again, this is kind of a binding process. You're actually saying, I want this routing policy, right, to bind to the gateway I just created. So once the HTTP request comes in through the gateway, look at the rules that I define here to figure out how to route it. And in this case, we use a destination, and we specify the host name webfrontend.default, because obviously it's in the default namespace. And that service is listening on port 80 as well. So that's the port number to use. So we're going to apply this, and there's not much to it. K apply -f artifacts web frontend virtual service. And again, we could do a kubectl get virtual services. And notice here, you can actually see that the virtual service is bound to the front end gateway, which is what we want, using the wildcard matcher on the host name, which means that even if we use an IP address, it should match. So if I refresh this page, notice now, this is not a TLS connection because we haven't done anything with certificates, but we're actually routing the request all the way to that web front end. So behind the scenes, web front end is calling customers, getting the JSON back and rendering this HTML table in all of its beauty. So so that's the lab in a nutshell. There's really not much more here. There's some candidate follow-on exercises that we decided to sort of suggest. You know, if you want to take this further and set up a DNS entry, you can do that. If you want to configure TLS, we give you the link into the Istio docs that sort of walk you through how do you configure a TLS ingress gateway. And that'll get you going in the right direction. All right, so I think we've just arrived at a good stopping point, about halfway through our workshop. So maybe before I let you go, just a quick question: how's everybody doing? Is everything going well? And please do let us know. And if there is nothing else, what I'd like to do is call a 15-minute break. And so right now, well, you know, everybody knows their local time. Right now here in Texas, I'm in Texas, it's 10:50 p.m. I'll be back at 11:05 p.m. And okay. All right, well, I hope everybody had a good break and you were able to grab a cup of coffee or whatever it might be. I'm going to stop this timer and let's jump back into it. So where did we leave off? Let's take a look at our sort of outline of labs. So we're about halfway through. We've got our environment set up. We've got Istio running. We have deployed an application. We've exposed it, right? And the last when we left before the break, we actually were able to use our gateway IP address to actually visit the web front end. So if you're there, you're caught up and you're with us, and and you've got your application deployed and it's using Istio. Now, all of the benefits of Istio we're about to discover through these upcoming labs. So we just did ingress. The next one is called observability. And let's talk about it. I've got just a couple of slides. I think this is, again, the bulk of the learning is going to be in the lab proper, not so much in the slides, but the things that are worth calling out. If you remember this picture of the two services, A trying to call B, and they each have a sidecar. What do these sidecars do for these applications, right? Imagine, maybe you're doing this today already, the typical application that needs to have monitoring, you need to actually either send metrics to your monitoring system, or you need to expose what they call a scrape endpoint for your monitoring system to be able to grab the metrics periodically from that endpoint. You have to instrument your application. With Istio, Envoy takes care of that. So that sidecar actually exposes a Prometheus metrics endpoint already. And so Prometheus is able to get all of the metrics. Now, how does Envoy have those metrics? Right, it collects them because all the traffic actually goes through the Envoy. So it knows how long a request took. It knows what requests came in, what requests are going out. So it's able to derive a very rich, long list of metrics. And it's a uniform set of metrics out of every single sidecar. So that's very powerful stuff. So along with metrics, we also have distributed tracing, which complements the observability picture, so to speak, that lets you view what they call distributed traces of calls through your application. And it's done by sampling requests. Usually it's about 1% of requests that are sampled in order to build a picture of all of the sort of end-to-end flow of a request, the path of the request, or the journey that the request takes from its start to the end and back. And along the way, we can capture information about like how long each of these requests took. There's this concept of a trace being made up of a number of spans, which are segments, so to speak, in this journey across multiple services. We can use the sidecar similarly for, again, shipping logs to some target backend, whether it's some kind of log service like your Elk Stack or what have you, or something running in your cloud. So you can, again, the same pattern. We don't alter anything. The pattern of having a sidecar not only solves the problems of the service discovery and the load balancing and retries and timeouts, but also the gathering of all the information necessary to actually monitor your environment. And so, that burden is completely taken off the shoulders of your development teams. And that's the compelling thing to me. All right, so armed with that knowledge, let's do our observability lab, which is really a whirlwind tour of all of the observability, not all of them, but the majority of the observability features you're going to find in Istio. And so the lab begins with a simple step of installing what Istio calls these add-ons. So it already provides all of the YAML files to deploy a number of subsystems that provide observability. Zipkin for distributed tracing. You don't have to settle for a Zipkin. There are alternative implementations like Jaeger, for example. Prometheus is what we're going to be exploring, which collects your metrics, and Grafana, which then uses those metrics to then display dashboards that allow you to monitor your system, and Kiali, which gives you terrific visualizations of your mesh and the services within your mesh. So we're going to begin by installing these things with just a kubectl apply-f. And these files we will find in the Istio distribution. So again, that Istio 112 folder that we downloaded in the first or second lab, rather, has a sample subfolder with an add-ons subfolder, and you'll find those files in there. So we'll do that first. And then we're going to use a specific command called istio-ctl dashboard. And that's basically you can run the help on it to actually learn a little bit how to use it, but it's rather simple. You can specify which dashboard you want to access, and it sort of sets up the ability for you to sort of access the dashboard from your system. Now, the next piece is rather interesting, which has to do with if you're going to observe something, you've got to have something to observe. That is, there are going to be some requests, some load generated against our application in order to be able to monitor it. And so in this workshop, we're going to use a tool called Siege, which we're going to install very quickly in our Cloud Shell, and we give you the instructions to do that. And once you do that, then you can rather use the Siege command. And here's an example. To actually run a light load against your application. Notice that the target URL is your gateway IP, and we're going to run it for about 20 minutes. That should be sufficient for the duration of running this lab. And then we're going to explore each one. So why don't we just dive right in and just take a look. All right, so step one, if you recall, if we look at our directory structure, we've got this Istio 112 directory with a samples add-ons subfolder, and in it you find all of these YAML files that you can apply. So -apply-f. Let's start with Zipkin, and then we carry on and apply the others. We're going to apply Grafana, Kiali, and Prometheus. -apply-f. Maybe we'll start with Prometheus, not that it matters. And then -apply-f Grafana and -apply-f Kiali. Okay, so these are going to take a little bit to come up, maybe in the order of maybe 10 seconds or so. Get pod. Get pod. Now these get installed in the Istio system namespace. Okay, so there they are, and you can see some of them are running already, but not all of them. Okay, so these are going to be our observability dashboards, observability systems, and they work in concert with Envoy to collect all of this information from the running services. So we need Siege. I think that's our next step. So how do we install Siege? Again, we have this conundrum of wanting to install it not in its usual place, because otherwise it's outside our home directory, and in Google Cloud Shell, it could end up being uninstalled. So let's just follow these directions. We just download Siege. We're going to unzip it, and we're going to install it. That'll take not too much time. Let's just go ahead and do that. So wget will download the zip file. There it is, Siege latest. And then the next command was just untarring it. Let's go ahead and copy that command. And that should give us a folder called Siege containing the source code that we're going to build, okay? And that sounds really scary, but it's really not. We basically run this command called configure, and we're going to configure the thing to install in our home directory so that it meshes well with the Google Cloud Shell. So we run the configure command. I'll let that run, and that's followed by a make command. Great, it tells us what to do, so I don't even have to. Okay, so make, and then make install. And once you run make install, the Siege command should be available. And in your path, it should be in your home bin folder. So if you look in your bin folder in your home directory, you'll see Siege in there, and that's what we want. So we've just installed Siege. So let's put it to work. How do we run it? So you can always run Siege help to find out a little bit about the CLI. That's never a bad thing to do. Lots of options. And let me just walk you through what exactly this particular command does. It basically says run 3 concurrent requests with an average delay of about 3 seconds between them. So if you tally it all together, it's about maybe a request per second that you're going to run against the gateway IP. Again, you might want to double check that your gateway IP is set. We put it in our bash RC file, so we should be okay. And now when this runs, it's going to look something like this. You see a bunch of requests scroll across the screen. It's going to be a blocking operation, obviously, and it's going to run for 20 minutes or so. And now we have a load that's running against our application. And what I personally prefer to do, you can run this in the background if you like. I prefer to just let it run and see it and keep it in the foreground and just use multiple terminals in order to be able to run other commands while at the same time our Siege is running in the first terminal. So that's sort of the setup I tend to prefer, but to each his own, so to speak. So let's explore each of these dashboards in turn. The first one is Kiali. So the command is istio cuddle dashboard Kiali. Pretty simple, right? You can run help on it to see exactly your different options. We're going to explore most of these. And so the first one's Kiali, and you can just click on this link to sort of bring up the dashboard. All right, so the way this works, Kiali has multiple different sections, but by far the most compelling one is the graph. What you can also see your services and your workloads in here, perhaps, but we haven't selected the namespace, so maybe we should do that, right? We know our application is running in the default namespace. So the moment I do that, things start showing up. But really the interesting aspect of Kiali is the graph, as you can already tell. Now I'm going to customize it slightly. I'm going to pick, you can see there's lots of options. I'm going to pick just a simple app graph, and maybe I want to turn on displaying maybe a traffic animation and security information. That might be good. You might want to also toggle the legend to understand what some of these icons actually mean, and take a little bit of time to understand that. But the things that I glean from just looking at this, obviously you could see the flow of requests. This is live. That is, if I were to turn off Siege right now, within a few seconds, maybe 15 or 30 seconds, which is the interval that Kiali uses to refresh what it sees, all of this will cease and stop. So these are live requests going in from our ingress gateway to the web front end, and finally to the customer's back end. So this is very useful. What else can we see here? The fact that that line is green means that the request is actually healthy. And you can see it here on the right-hand side as well, that HTTP requests all are successful. They're okay. They're 200 responses, right? And the final thing I point out is the little lock icon shows that all of the communication across this trace is encrypted with mutual TLS. So that's Kiali in a nutshell. There's obviously much more to explore, and that's what I want to give you the chance to do in the lab when you work on this lab for yourself. Definitely poke around and look around and try different features. You could turn on namespace boundaries if you like, but that's Kiali. All right, so let's move on from Kiali to a different maybe dashboard. Let's look next at Zipkin. All right, so I go back to my Cloud Shell. You can leave Kiali running if you want and open another terminal. I'm going to Control-C that, and I'm going to, again, run Istio dashboard. And this time, I'm going to pick Zipkin. And Zipkin runs, its canonical port is 9411. And the interface looks like this. It looks rather minimal, but the basic idea is to click on this plus button. And you can pick a service. Let's pick, say, the web front end service. And you're going to click on this button here called Run Query. And what you see here is a list of traces that have been captured. Now, some of them have 2 spans, some have 4 spans. This is probably going to be more interesting because you can actually see a full sort of flow of a request from start to end. So I'm going to pick this one right here. And you can actually see all the actors. So this is our distributed trace. It sort of feels like a stack trace, but it's actually across these network boundaries, right? You have the request from the ingress gateway to the front end, and then the front end turns around and makes the call to the back end, which is the customer service. The other thing that's worth pointing out here is the durations in each span are actually called out. So this is very useful, this tool is, for diagnosing where your latency is, right? Which actual service in this sort of distributed trace is actually responsible for the bulk of the time consumed. Now here we see the whole request end-to-end took less than 15 milliseconds, so it's actually really good. But you kind of get the idea. I think you can zoom in on each one of these spans. There's some metadata here on the right-hand side that gives you more information with respect to each of these. There's ways of looking at a subset of the trace and just looking at, say, I don't know, a couple of the spans and sort of filtering out the others. And that's Zipkin in a nutshell. Again, when you have a full-blown microservice environment, you can imagine that the scenario becomes much more useful because you don't have just 3 or 4 spans, but maybe a dozen or more spans that compose your trace. All right. Now there's, you can do searches, you can look for specific calls. There's this notion of a trace ID, which is a unique value that essentially propagated through HTTP headers. And that's how this feature is actually able to function, is that unique value is used to sort of correlate multiple HTTP requests under a single trace. And that's called the trace ID. And then every span has its own span ID as well. Okay, so let's carry on. That was Kiali. Now, Prometheus is rather interesting. And we begin by, instead of just opening the dashboard, we are going to look at, here, I'm going to grab the name of my customer pod, and I'm going to do this. We're going to do this together. Once we have the customer pod name, then what we can do is run a command like this. What does this command do? Let's decipher it together. We're actually asking for the Prometheus endpoint that's exposed by the sidecar. So our application never exposed port 15090. That's actually supplied by Envoy. And if we run this call, now I'm expressly scoping this request. I'm doing a grep on it to filter out a lot of the output, because there's lots of metrics that are being returned as a response to this request. But here you can actually see the total number of requests. There's a counter metric that's actually relayed back to Prometheus through this endpoint. So Envoy is doing that for us, which is terrific. And the reason we see two of them is because these dimensional metrics have different values between the first one here and the next one there. So that's really a strength of Prometheus. And we can give you an example. So when we run our dashboard, let's go ahead and run this dashboard. Maybe I'll close some of these other tabs while I'm at it. And we're looking at the Prometheus user interface. We're able to run some queries, which is rather interesting. So if you just start typing Istio, you'll see a whole bunch of metrics that pertain to Istio, and that's a good sign. That means these metrics are actually flowing from your services all the way back to your this Prometheus metrics collector, right? So what is the lab asking us to do? It asks us to look at total requests. Istio requests total is the name of the metric. So Istio requests total. And that's a counter. And we just see a whole bunch of information. Now you see some of them have many more hits on the right-hand side than others, because again, this is all the same counter, but with a different set of dimensions, of tags, metadata associated with them. It's much more interesting to look at the graph, right? And you could see that when we started running Siege, some of these numbers, since this is a counter, it's ever increasing. And what we can do with some of this metadata is we can actually say, show me all requests that have a response code of 200, right? So you can look for errors, for example, if you're looking for 404s or something like that, you can actually filter this, right? Which is kind of cool. So the number of 404s is rather small. I think that's probably before we set up our ingress gateway. Maybe we had some 404s, I don't know. And with counters, what's more interesting is looking at the rate, right, of requests over time. So we can ask, this is what's called PromQL. It's a Prometheus query language where you can invoke functions to actually get information. So if I were to tell Siege, for example, right now to sort of increase the rate of requests against our load against our system, you would see those values would actually go up. But honestly, Prometheus is really primarily used not for its user interface as much as for its ability to collect these metrics. And Grafana is used as sort of the canonical interface on top of Prometheus. And that's where things get really interesting, in my opinion. So let's go and take a look at Grafana. So let's open the Grafana dashboard. Now, again, this is, I think, a classic example of where Istio shines by giving you a homogeneous view of your whole mesh, because every single service you deploy, it doesn't matter what service it is. In this case, we have a customer service and the web front end. The same set of metrics are being collected for all our services, and the same sets of dashboards can actually be used to monitor them. So what we basically see is that we didn't have to design these Grafana dashboards. We get them for free, which is wonderful. Okay, I'm going to pause for a second. Okay. And so what we see here is a stock list of dashboards that we can start utilizing. Now, the first one here is actually for monitoring the control plane itself, which is kind of interesting by itself. I'm going to skip it and look at the mesh dashboard. This is a good sort of high-level overview of, is my mesh healthy, right? You can look at the global request volume, the number of operations per second, the global success rate. If you have errors like 500s, 400s, you don't have any, that's wonderful. Virtual services, destination rules, we'll talk about those in a minute, and other things which are currently not applicable because we don't have any of them. So if we configure authorization, authentication policies, you should see some information in some of these boxes. Right now we don't. So this is a good dashboard for looking at the health of your mesh. And again, if we go back here to this list of dashboards, we can look at the service dashboard where it gets a little more interesting. We've got 3 panels here. And you can look at the request volume for a particular service. So you can look at the customer service, you can look at the web front end service. You can see the request durations in terms of how many milliseconds they took, and you can look at different percentiles, whether it's 99% of requests took less than a certain amount of time to return a response. You can look again at the success rates for that particular service. You can sort of zoom into a particular service through here, and you can look at there's some more graphs here that show you more information, incoming requests, and you've got different series of information that you can sort of parse through. And then at the most granular level, you have the workload dashboard where you can look at a single workload. So again, we're going to pick a namespace here, the default namespace, and we're going to pick maybe customers v1. Maybe we'll start with web front end. I like to point out here the fact that you've got a panel with general metrics, and then you've got a panel for inbound workloads. That is requests to the web front end. But you also have another panel showing you outbound services that are being called. And we know the web front end is calling the customer service. And so we could actually sort of confirm that here by looking at some of these graphs. So we're calling, there's outgoing requests from web front end to the customer service. Are those healthy? How long are they taking? What are the target services that are outbound from the web front end service? Now, if we look at the customers v1, notice there is no information in the outbound panel, and that's because the customer service does not call any other services, but it definitely has inbound workloads, right? So you could see the sort of things from the perspective of the caller or the callee. All right, so Grafana really gives you a complete suite of dashboards that let you monitor the health of every single service and every single workload, and it's terrific. And I hope this gives you just an overview of some of the sort of out-of-the-box capabilities that you get with Istio. All right, so definitely take the time to explore these dashboards on your own. Do the same thing I'm doing. Essentially, you install Siege, you run Siege, you have a load running against your system, and at the same time, you can run these dashboards and you can actually see a bunch of useful information. Okay, Peter, how are you doing? How are we doing?
I'm well. There's a just question came in. So that all these observability pods components are meant to monitor the Istio components or the whole cluster. So it's monitoring everything that has an Envoy proxy injected, right? So it's monitoring your applications, right, that have Istio proxy injected, but there are dashboards for monitoring Istio installation itself. So you can look at I think Istio-D has its own dashboard. You can look at the number of successful, failed pushes of configuration. There's a dedicated WASM extension dashboard, right? So it's both, but it's not necessarily, the whole cluster is kind of odd, right? Like if all your namespace, if everything that you're running in your cluster has a proxy injected to it, then yes, you are effectively monitoring your whole cluster. But it's just pretty much you're monitoring any workloads that have the proxy injected. So all the metrics. Do we have other add-ons for monitoring tracing metrics other than it's given in the slide? So those are the
ones. That's right.
The default ones that are included. You can you have a choice of, I think, in addition to Zipkin, you can decide to install Jaeger if you want. I don't know if there's anything else in extras though. If you go to that folder, I have no idea. No, it's just Prometheus and Zipkin. But yeah, so these are the add-ons that get installed. They're a part of it. They're shipped with Istio, right? Like the installation ships with Istio. I don't know if you had any like specific add-ons that you had in mind, but if you think about it more, like since you have Prometheus, a lot of tools, observability monitoring tools, also integrate with Prometheus already, right? So
yeah, and I wouldn't be surprised if other competing tools also provided their own sort of YAML files that you could work with Istio.
Yes,
because they want to be able to play in that.
Yeah. But I mean, to be completely honest, these tools are not necessarily working with Istio at all, right? They're just talking to Prometheus, right?
That's the beauty of it,
metrics, right?
Yeah. So there's no coupling between your applications and the functioning of these things. These are out of the box products that do what they were designed to do. They weren't customized in any way to function. In this environment.
So if you have any other like tool like Grafana, if you wish, or something that depends on Prometheus, it's just a matter of installing it and then saying, hey, here's my data source, Prometheus data source. Use this Prometheus instance as a data source, and that's it.
Yeah. Okay. All right. So where do we go from here? We talk about observability, and we talked about the fact that there are multiple cross-cutting concerns. Observability is one of them.
So one more question, injecting multiple. So there's no, so the question is, injecting multiple observability containers as sidecars doesn't increase the traffic in the cluster. So there's only one
sidecar
proxy, one sidecar that gets injected. It's just that one. You don't have to inject more stuff, right? With your single workload, you're just injecting one sidecar each, right? Now the question, increasing the traffic in the cluster, I haven't looked at the latest numbers. I mean, it does, of course. There's multiple hops because it's not just service to service. It's Envoy to service, and then service to Envoy, and Envoy to Envoy, and Envoy to service again, right? So there are multiple hops, but I think it's
nothing here is really out of the ordinary. This is what teams do to monitor their services. The one thing to watch for is typically when you deal with distributed traces. When you work with Zipkin, the default is to sample on a very small percentage of all requests, specifically to avoid this ballooning of traffic. So typically with Zipkin, you configure like a 1% sampling.
Also, just quickly on, like, I just Googled the numbers really quickly. So the load test that they did with Istio 1.13, and that's the latest, right? So they had 1,000 services and 2,000 sidecars and 70,000 requests per second. And Envoy added 2.65 milliseconds to the 90th percentile latency, right? So,
wow.
And the CPU usage was 0.35 vCPU and 40 megabytes of memory per 1,000 requests per second. They're going through the proxy, right? I mean, it adds, right? Of course, it adds latency, but
it's
going
to be fine, right? For 99.99% of
I think so.
situations.
Yeah. Unless you're like really performance sensitive with your stuff, then you should probably do your own like load test and make sure, right? But for majority, it should be fine.
Yeah. And think of the alternative, right? I mean, most systems that we build have all of these cross-cutting concerns are coupled into the application logic. It's not scalable at all. And so I think when you use Istio, the fact that you can have all of these concerns work in harmony without actually having to instrument your apps, without having to, there's no extra overhead in terms of work or burden that you have to sort of modify your apps in any way. Whereas I think before Istio, you didn't have much of a choice. And yeah, well, there's more we could say about that. Maybe I'll cap that conversation right there. All right, so speaking of cross-cutting concerns, observability is one. There's two other big ones that we're going to discuss. One is traffic management, and the other one is security. Now, security is a big topic, and I don't think we're going to have time to cover everything about security. I'm going to touch on a few things, and I think I'm going to err on the side of not bombarding you with too many slides, but maybe just the essentials. So I'm going to go maybe halfway through some of these, the security section, and then we'll maybe skip ahead to the lab. So the things that are, I think, important to mention is the fact that in a service mesh, workloads are identifiable. So what are our workloads? It's web front end and customers. And how are they identifiable? It's usually based on the service account. But every workload is a unique identity, and there's a standard called SPIFFE, okay, which stands for Secure Production Identity Framework for Everyone, which is implemented in Istio, which basically leverages mutual TLS. So basically that means that there is a certificate that is generated and assigned and rotated automatically, by the way, for every single workload that's running. But there's also the standard called SPIFFE, which basically defines a way of a naming scheme, right? And you can see an example there. There's a SPIFFE : cluster.local / and basically what this does is it provides sort of a uniform URI, right, for a resource defining the identity for a service. So this particular service is defined by two things: a namespace it's running in and the service account that is associated with that workload. And that's sort of baked into the certificate. And so imagine, some service receiving a request. What Envoy actually does is it looks at the certificate and looks at that identity, and it knows who called it. So that's very powerful, because once you have identity, you can talk about authentication, right? So there are a number of modes in which you can control the way that communication happens inside your mesh, right? When the client calls a server, we're all familiar with TLS. If you're not familiar with mutual TLS, it's basically doing the same thing from both ends. That is, not only does the server identify themselves to us, which is the case use case we're most familiar with when we go to some website, for example, but we actually authenticate ourselves vis-a-vis the server by sending them our certificate as well. So it's more of a peer-to-peer type scenario, and that's called mutual TLS, right? And that's really the foundation. Now, the mode in which Istio runs by default is what's called a permissive mode, which basically says that every Envoy that receives a request will allow both mutual TLS communication and plain text communication. And that's permissive mode. And that's done on purpose to sort of help companies that are onboarding onto Istio that are not yet ready to turn on mutual TLS everywhere to maybe provisionally allow plain text traffic in addition to mutual TLS traffic. And there's, again, another mode called strict mode, where you explicitly forbid that. So you can configure that. This is authentication configuration, and it's called peer authentication. Okay, so peer authentication, you can pick whether you want permissive or strict, and you can pick those options at any sort of level of granularity you choose. So if you want to apply it only to a single namespace, to a single workload, you could say this particular service will only accept mutual TLS, but another service will be more permissive, for example. You can do that as well. So here are some examples of what the YAML looks like. So it's the kind is peer authentication. Here we're saying for the namespace foo, we want to apply the strict mode. Here we're saying we're being more specific. We're saying for this particular app that's labeled, that matches this label, or multiple apps that match that label, we're going to use strict mode, or we can even go even more fine grained and say only for requests on port 5000 for a particular app do we want to use, maybe or maybe we want to use strict mode for any other port, but not for port 5000. Now, for users, how do we authenticate users? The basic idea is that user identity is embedded in the JOT token that was somehow, through authentication, through user authentication, was sort of generated and then relayed with every HTTP request. And so the primary mechanism is basically you have this notion, again, another Kubernetes kind called request authentication that basically defines that you have a particular JOT issuer and that the actual JWT token can be extracted from the header, and we can use the information in that token to look at the identity of the caller, of the user, right? So there are claims inside these tokens that allow you to look at the subject and the email and so on, and other claims as well. Now I'm going to fly through this because security is a big topic, and I don't expect anyone to sort of get all of this in one go, but the information is there in the slides. So here we see this is an illustration of exactly how this actually works behind the scenes. When you define a request authentication, what actually happens behind the scenes is an Envoy filter is actually applied to the sidecar that essentially interprets the JOT token. Basically, we can identify users and we can identify workloads. I'm going to skip over this slide for the sake of time. I want to make sure we get through everything. Now, along with authentication, we have authorization. So there's another Kubernetes kind called an authorization policy, and we can construct these authorization policies to say, service A can't call me. I'm service B. I'm only receiving requests from service C, for example. You can also say I require users to be authenticated before they access me. So there's two facets to authentication: the principles and the request principles. The principles identifies the actual workload, and the request principles identify the actual humans, the users that are in accessing these services. So here's an example authorization policy, and it looks like it's maybe hard to decipher, but what this particular policy says is I require users to be authenticated. So the keyword request principle that you see on that last line essentially references the actual end user, the JOT, right? I don't care who it is, but they have to be authenticated. So if they don't have a JOT, I'm not going to allow the request. Sorry, I kind of skipped over. Sorry. So what else? I like this particular slide because, okay, so the way you define authorization is there's a number of fields underneath the rules field. And the first one is from. So basically what this says is I'm going to allow requests from the namespace called prod. I'm going to allow requests from workloads whose name, who use the service account workload. And then I'm going to allow requests that come from the user, Peter J. There's a from section, there's a to section that can actually be, again, the granularity, I want to apply this only to particular requests to specific paths, so using specific HTTP methods or ports. And there's a when section that actually can get even more fine-grained in terms of under what conditions do I want to apply this authorization policy. I'm not going to go into these details because I think it's a little bit too much. There's a final field called action, which basically says anything that matches whatever I've just specified, I want to allow, or I want to deny, or I want to do something custom, or I want to just audit that information. Those are the basic actions that are defined with the authorization policy. So we're going to get to play with this in the lab. I think I'm going to stop here and let's talk about the lab. Okay, so let's go to the security lab. And the security lab, I think, follows a fairly logical pattern. We begin by recalling that when we looked at the observability at Kiali specifically, there were these lock icons on every segment, so that we know that mutual TLS is being applied in there. And the first question that I'm going to ask you to answer is, can you concoct a scenario where you can test whether plain text traffic is allowed. So the way that we're going to do this here is by creating a separate namespace that's not configured for sidecar injection, which means that if we deploy our little sleep pod to a separate namespace that is not going to have sidecars, our sleep pod is not going to have an Envoy to help it set up a mutual TLS connection. It's not going to have a workload identity. And the only type of curl requests we can do from that pod are plain text requests. So we're going to call the customer service, and we're going to find out whether we get some kind of connection refused or whether that request is going to be allowed. We're going to find out, are we in permissive mode or are we in strict mode? And then once we find out that we're in permissive mode, by the way, we're going to then apply some YAML to actually turn on strict mode for the entire default namespace. All right, I see a question here that says, can you help me understand this? The peer authentication and authorization policy are built-in K8s objects. They're built-in Istio objects. So all of these custom resources we're talking about are specific to Istio. So they build on top of the base Kubernetes. So Kubernetes gives you the basic CRDs for, pods, deployments, and services, and so on. And Istio then adds on top of it the ones that I'm describing here, the peer authentication, the authorization policy, and so on. So I hope that answers that question. All right, so let's, I can keep going here and give you the outline, but why don't we just do it? Let's begin. Let's see. So the idea here, but do I still have Siege going on here? No, it's pretty much done, but I can continue working here. That's fine. All right, so we've got a bunch of pods. And notice here that second column ready shows that we've got sidecars. The 2 out of 2 basically means, okay, there's an Envoy with every one of these. But what if we create a separate namespace? How about we create a namespace called other NS, other namespace. And in that namespace, we're going to deploy the sleep pod. But because we don't label that namespace, we're not going to get a sidecar. So K apply -f artifacts sleep -n other NS. Notice I specify a separate namespace. So if I look at the pods in the other namespace, there it is. It's coming up. And notice the ready column there says 0 out of 1, right? Or 1 out of 1 now. That basically means we don't have an Envoy sidecar. So if I kubectl exec, so remember, kubectl exec is basically what it does is allow us to run a command from inside that sleep pod that I just created. So I have to specify the name of the pod, and maybe we'll do a curl to customers.default because it's running in the default namespace. And notice the response, it works. We're doing plain text requests, which means that if this works, we must be in permissive mode. So let's change that. Let's look at mtls.yaml and this little bit of YAML, which is an Istio CRD, by the way. And the way you can find out is the API version says security.istio.io, right? It's part of the Istio security umbrella, or I forget what that's called, the module. We're applying the strict mode for anything in the namespace default. So if we do kubectl apply -f artifacts mtls strict, how do we test this? We basically rerun our little kubectl exec command, right? And does it succeed now? And notice it doesn't succeed anymore. Now we get a response such as connection reset by peer. And that's because we're not making an MTLS request against the customer service. So it no longer works. And we can do the same thing against the web front end. And we should get the same result, right? Connection reset by peer. So this is how we sort of tighten security. And we say, okay, we want only strict TLS to our workloads. All right, so what's the next step? We can ask ourselves another question, which has to do with, here, let me pose this question. Does it bother you that even though only web front end technically should be allowed to call customers, any other pod that I deploy to any namespace can call customers right now if it has a sidecar, right? If it uses mutual TLS. And we can prove that, right, by doing what we did earlier, which is a kubectl exec from the sleep pod in the default namespace this time, right, to the, say, the customer's service. This is allowed, but the question is, should it be allowed? maybe I want to tighten that down. So imagine a scenario, a security scenario where somebody, the perimeter has been breached, and somebody who's maybe a bad actor is actually running something inside our Kubernetes cluster and trying to call our services. But we can actually define an authorization policy that says, no, we're not going to allow that. The only thing that should be able to call customers is web front end and nobody else, right? And so let's take a look at an authorization policy that defines exactly that. And it is right here. So notice the kind says authorization policy. We give it a name. We specify the default namespace since it applies to things in the default namespace. And we have a selector that uses labels as a way of matching who to apply that policy to. So we're saying this policy applies to any pods that have the label app customer. So that's the customer service. And the rule is, notice it has a from section. It doesn't have other parts, so it's fairly simple. The action is allow, and the rule says, if the request comes from the web front-end workload, notice the principal uses that spiffy identity we were talking about earlier. It has this combination of a namespace name and a service account name, and that's the service account for the web front-end. So if I'm making a call from the web front-end, let it through. But if I'm making a call from anywhere else, do not allow it. Right, so if we apply this is the auth-z policy customers. Let's do that. Let's do it. Okay, apply -f artifacts auth-z policy customers. Now, if we just repeat our kubectl exec command from the sleep pod, that should be denied, right? And notice it is. It says RBAC, role-based access control, access denied. Right. Whereas if we were, if we try to do it through the front door, if we, for example, come back to, where is my application? Let's see, Echo Gateway IP, I might have closed that. So if I grab my IP address and come in through the front door, this still works. Okay. Why does it work? Because my request went to the web front end. Web front end called customers. And because the web front end workload matched that authorization policy, it was allowed through and it got its response and it was able to return the list of customers. All right, so in this lab, I have a little challenge for you, which is I'm asking you to write a similar authorization policy, but instead of locking down callers to the customer service, can you actually lock down callers to the web front end to only allow calls from the ingress gateway to call the web front end? That's the challenge. So if you let's think through this together, right? We can use this as a template, right? Let's just do this together. See if I'm going to copy auth-z policy for customers to a file maybe called auth-z, that stands for authorization, right? Policy for web front end. How would we change that? Well, for one thing, we want to give it a different name. Allowed web front end clients, maybe. It is in the default namespace, but it should, or is it? Yes, I think so. It should match the label for the web front end service. So that's probably called web front end. We could verify the label for web front end. Let's do that real quick. Get pod-show labels. So the web front end as an app equals web front end label. So that's correct. So let's come back in here. So that's the right matching label. Now we want to allow requests if they come from the principal that matches our ingress controller. Well, the ingress controller is not running in the default namespace, right? So where is it running? Do you recall? It's in the Istio system. And what's the name of the service account? I don't know, but we can definitely look that up. So I've got a command here where we can actually look at the service account name associated with the Istio ingress gateway in Istio system. So if I just run this command, we could see the service account name is this guy right here. And so that's going to be part of that spiffy identity name. So if we basically doctor this field right here, and we put that, that should do the job. Okay. So here's an authorization policy that says the only person workload that can call web front end is the ingress gateway. So we can put it to the test, do k-apply -f auth-z policy. And there's two things we could do, a positive and a negative test. That is, if we come over here and refresh this page, does it still work, right? Or did we break it, right? And then the counter example, the negative test, is if I do a kexec from the sleep container and do a curl against the web front end, will it work? And we'll get an access denied. So now we've locked down through an authorization policy who can call what service, right? So this is even more secure than it was a minute ago. And that's the security lab in a nutshell. Okay. All right, let's see what questions we've got. Okay, I'm going to just touch base with Peter. Peter, how are you doing?
I'm doing good. It's good.
All right.
Yeah, I'm all good. I like the security, like the resources here, and the security area can be very daunting. There's a lot of things that you have to set, and from and to and when and all those things. And I
There's
mean,
a lot of options, a lot of knobs that we can turn.
yeah, a lot of options, and it's also security, right? It's always like at least making me nervous, right? When you're dealing with anything security related. I mean, one tip here in the security section is if you're doing this for reals, right? Not as this lab, right, or workshop, apply a policy that denies everything. Do that first, right? So you can create a policy that's gonna just deny all the calls between all the services that you have running. And once you do that, then you can go and explicitly allow service A to call service B to call service C, and so on. But yeah, awesome. Yeah.
All right. So we're now going to broach our last use case, which is yet another cross-cutting concern, which is traffic management. Right. And what I'm going to do this in a slightly different fashion, just to explain. I wanted to come up with a use case that's very realistic from sort of a development team standpoint for traffic management. And that use case is the fact that we've got an application deployed and we're ready to upgrade one of our services. So the development team has sort of cooked up version 2 of the customer service, and we want to deploy this in a very safe fashion with zero downtime. And how are we going to do this with Istio? So with your permission, I'm going to take a second and share my iPad. And we're going to draw this together just so that we understand what we're going to do. Okay, so hopefully you guys can see. This is a picture of an app that I have running in my iPad. And we're going to sort of drill into it. And I'm not a very good drawer, but let's try this together. So we have a picture of, let's draw what the state of the world that we have right now going on. We have incoming requests that coming to an ingress gateway. Right? We've got our ingress gateway, just like Kiali paints for us, although it does a much better job than I'm doing here. And then that request is being routed. And if you remember, the way that we made it route to the web front end is through a concept, an Istio custom resource called a virtual service, if you recall. Virtual service said route all requests to the web front end to a destination matching its host name. And we know that the web front end is calling customers v1. Okay, so this is customers, and I call it V1 because it's the first version of customers that we've deployed. Now, imagine how this actually works. Every time this, we had pictures of service A calling service B before, right? And the fact that we can have multiple instances of this guy, and there's some load balancing, and that we've got a sidecar here. Our Envoy sidecar is actually the one controlling, these outbound requests from service A to service B. If we were to deploy V2 alongside V1, so if this were customers V2, the problem is that both customers V1 and V2 have the same labels. Well, not exactly, right? There are two labels applied to each of these deployments or these pods. One is the app label, and the other one is the version label. And these are canonical names, by the way. Typically with Istio, you want to use the app and version label. The app identifies the service name, and the version, its version, of course. And they both share the same app, customers. The difference is the version, V1 and V2. And so if I were to deploy V2 right now, what would happen is, from the point of view of the web front end, traffic could end up going to both V1 and V2, and that's something I want to prevent, right? I'm the cautious developer that I am. I want to be able to dissociate those two things. That is the act of deploying my application from the act of directing traffic to it. And that's a very important thing to be able to do. And if you're able to do that, that gives you special powers, right? You can do blue-green deployments, canary deployments, you can test applications, you can be like Netflix, basically, right? You can siphon off specific requests that have maybe specific qualities, maybe a custom header or custom cookie, and you could say, I want to route that differently than the way that I want to route something else. You can do tests in production. It just opens a whole window for you to try different things that you could never do before in a very more sort of stratified environment. So how are we going to do this, right? Istio to the rescue, so to speak. It introduces two concepts. The first one is a destination rule. That's the name of a custom Istio resource that allows you to define multiple subsets of any service. So you can actually say that I have the customer service, right? But I have two subsets, V1 and V2. And by just defining two subsets, then you can use these subsets as an input to the definition of a routing rule, which is done through another custom resource called a virtual service. So those things work together in concert. So we're going to define a destination rule. That's going to be our first step. And our second step, we'll be able to define a virtual service. What virtual service will say is route all requests to customers to subset V1 and do not route anything to V2. That's what we want. That's the picture that we want. So we've got actually a much nicer illustration of this in our slides. So maybe I'll go back to our slides. That's the idea. That's what we want to begin with. That's what we want to accomplish. So I'm going to share my slides again. Let's go back to our web browser. I think it's this guy. Right. So we're talking about virtual services and destination rules. And I want to find an example. I'm going to skip over this. This is a great diagram, but this is what a destination rule looks like. Notice we define multiple subsets. We can hear what we basically say is you could tell V1 apart from V2 by looking at the labels. If there's a label that says version V1, that pod belongs to the subset named V1. So it's very logical, I guess. And then step two is a way of utilizing those subsets for routing purposes. And that's where the virtual service comes in. So in this case, we're saying we're going to route 70% of traffic to the V1 service and 30% to V2 or something of that nature. And that's all I want to do with respect to the presentation. I want to hop right into our lab and just start exercising some of these ideas. So let's kind of get a lay of the land. The first thing I want to do is just looking at the labels that are sort of assigned against each of our workloads. So if I look at my pods and I look at the app label and the version label, you can definitely see what labels are applied to each of the two pods. And that sort of makes sense. And we're going to introduce a V2 and we're going to have to deploy it. But before we deploy it, we want to be able to safely deploy it. We're going to make sure that all traffic goes to V1. And then we can deploy V2 and it will receive no traffic, but at least it'll have been deployed. And that's half the battle, so to speak. We're sort of divide and conquer. All right. And so here, if we look at the customer service, we can definitely see that the selector for the customer service is app equals customers, which would otherwise match both V1 and V2, which we want to prevent. So we start with this destination rule. We've already looked at it. It basically says that there are two subsets. Okay, so let's do that. And that you'll find in your artifacts folder. So we can do a k apply-f artifacts. And the name of the file is customers destination rule. So this is specifically for the customer service. So when we're saying there are two subsets, so we can look at the destination rules. We have one defined called customers, and we can do a describe. And that's just going to parrot back what I just gave it, that there are two subsets you can see at the bottom of the screen, one called V1 and the other one called V2. All right, so that's the first step. The second step is to then say we want to route everything to the subset called V1. so that we can then safely deploy V2 without worrying about our customers seeing maybe a half-baked implementation. Maybe we haven't tested it yet in production. We want to be able to test it in production. All right, so that's what we want to do. So that's the customer's virtual service. So K apply-f artifacts customers virtual service.yaml. And again, let's take a look at it together so we understand what we're actually saying. We're saying route everything to V1. So now that we've defined the subset, we can actually use that subset in this sort of routing rule. Now, there's other things you can specify here, and for the sake of time, I'm not going to be able to get into all of that, but you can define other things that pertain to how things are done, both in virtual service and in the destination rule. So if you look at the destination rule, we can specify in here, I know, things like a number of retries against each subset, or load balancing policy strategy for round robin versus least request, or something fancier than that. You can do all of that in there. Okay, so how do we test this? Let's think about this. If I deploy V2 and I turn on Siege and I send a whole bunch of requests to the web front end, all traffic should go to V1, right? Now, visually, when you look at V1 versus V2, the way that you can tell them apart is V2 adds a second column to this table, which is the city in which the customer resides. So it's easy to tell them apart. And right now, if I refresh this page, I'm only seeing V1, but I haven't yet deployed V2. So let's do that next. Okay, apply-f artifacts customers v2.yaml. Now, if we look at our pods, it's definitely coming up. We definitely have. And if I do a show labels or -l app, you can definitely see that now they both customers v1 and v2 match the customer's app, the app equals customer's label, I should say. Now, let's run Siege. So here we go. That's the same command we were running before, which is going to send a whole bunch of traffic to our application. And while traffic is going, we can turn on Kiali. That can tell us, that's an easy way to visually see that is any traffic going to V2. So let's do an Istio cuddle. If you recall, let me go to the top here. Istio cuddle dashboard, Kiali. And again, we'll open that and we'll go look at our graph. And maybe this time we want a versioned graph so that we could tell V1 apart from V2. And it looks like all requests are going to V1. That's a good sign. We can also manually check. We'd come over here and refresh this. We've deployed V2, but no traffic's going to V2. So that's good. So what's going to be our strategy for very carefully testing that V2 is working by just maybe putting a custom header in our HTTP request that our customers won't be using, maybe a debug header, and just testing V2 in production before our customers see it. That's going to be our first sort of port of call. Once we've established that V2 is actually working correctly, then we can start siphoning maybe 10% of requests to do canary to V2, while 90% of requests still go to V1. And then we can look at our monitoring dashboard to see, well, does V2 have any performance regressions or anything like that? And if it doesn't, then we can slowly increase the responsibility we give, the amount of traffic we funnel over to V2. That's the idea. So we have a number of progressive pictures of a virtual service that defines slightly different routing policy, so to speak. So this virtual service is going to replace the one that we currently have, which routes everything to V1. This says with the match condition or field on line 10, it says, you know what, if in the header you find that the user agent is called debug, okay, and this is a little bit fictitious, but you could use that in a very similar way to only allow requests from developers, for example, that have a particular cookie or something of that sort, then route the request to V2. But otherwise, just fall through to what we see on line 18 through 21, which is route everything to V1. So let's first apply this. This is called customers v2 debug.yaml. So let's open another tab, and we're going to do a kubectl apply-f artifacts customers v2 debug.yaml. Okay, so that basically means if we go here to our web page and we refresh it, notice that all requests go to V1 because my user agent is Chrome, it's not debug. So how do I change that? I can use my your basic Chrome tools, the developer, what is that called? Developer tools. Oops, let's see. Here we go. And there's a specific panel here called the conditions, the network conditions, where we can actually say the user agent, we want to customize it. We want to set debug. And when we do that and we refresh the page, notice that now the routing policy sends all of our requests to the V2, but we're the only ones that are able to test that V2 is actually working. So we're just testing the functionality of V2 before we're actually sending any customer traffic to it. So mission accomplished so far. V2 seems to be working, but we don't know if it works under load. Now, an interesting thing you could do, if you refresh this like 10 or 20 times really quickly, you might actually be able to see, there we go. We actually see the Kiali, notice that some requests are actually being sent to V2, which is kind of cool. Now, if I just wait, I wait like 15 to 30 seconds, I'm not sending any requests to V2 anymore. And what you'll see is this diagram will collapse and all requests will look like they're going to V1. Okay, let's just wait and see that. I think that's worth seeing. So that just takes a few seconds for Kiali to get kind of an updated state of the world. Remember, the majority of traffic is actually coming through from Siege. All right, so what are we going to do next? We're going to modify our virtual service even further. And maybe we'll let this guy refresh while we do that. We'll come back and revisit in a minute. So there's another version of the virtual service that I call Canary, which basically now is not going to use a custom header anymore. We're going to remove that custom header altogether in our policy. And we're going to say, let's just send 10% of traffic to V2. Why not, right? And that'll overwrite our existing virtual service. So if we look at our virtual services, we have the one called customers. And if we apply -f artifacts customers V2 Canary, what we're doing is we're saying let's send 10% of traffic now to V2. Now, how do we know? Well, we could definitely just try to, let's just remove we're going to go back to using the browser default and refresh this. And about 90% of requests should go to V1. I'm refreshing the page multiple times. And again, the majority of them go to V1 and about 10% of them go to V2. Another way that you can do that, and you can definitely see that some traffic is going to V1, V2, is we can open Grafana, right? And that's really where we should go next in terms of making sure that from a monitoring standpoint, V2 is actually healthy, that it's actually able to sustain the load, that there's no major latency in those requests. So let's do what is it? Istio cuddle dashboard. Grafana. We go over to Grafana. And what do we want to look at here? We want to specifically look at one workload. So there's a specific dashboard for that. We're going to look at the Istio dashboard. Make that bigger. Here we go. Called the workload dashboard. And we specifically want to focus in on customers V2. And first of all, we want to see, well, are there any errors? No, that's good. What's the request duration like? 5 milliseconds? That's excellent. So it's doing well, right? Inbound workloads. That all looks good. We know there are no outbound workloads for the customer service to begin with. So now that we are able through observability to ascertain that the new version of our service is actually healthy, handling so many requests, why don't we just up the number of requests? And that's what we're going to do next. So we can do a very simple, how about a kubectl edit virtual service? And what we want to do is just alter these numbers, these weights. Maybe we give it 20% of traffic now. Maybe we'll go to, we'll be bold and we'll go to 50%, right? We'll do a 50-50. And as we alter that balance, we're actually doing a canary deployment, right? And we come over here, and as this refreshes, notice the number of IOPS, of operations per second, rather, increases from 0.1 to 0.9. So you see that we can start to see over here an ascent in the graph. Something's going up, right, in terms of number of requests. So the number of requests is going up, but all of the other metrics look healthy, right? We don't have any 500 errors. Our latency hasn't gone up. It's all pretty much looks the same. Obviously, we don't have that many requests. We can have fun and just maybe modify siege parameters here. And where's siege over here? And maybe instead of 3 concurrent requests, we can make it, I don't know, 10 concurrent requests. And then we can also wait a few seconds and see the number of requests go up. Oh. Okay, I'm gonna ignore that. Okay, so the number of IOPS is going up, but the health of this service looks good, which means that we can go to the next step and maybe transition all traffic over to V2. We can also just really briefly just hit the web front end. We should see about 50% of requests go through to V2 and 50% to V1. And then the final coup de grace, which is we can rerun this kubectl edit command. And maybe now we're ready to transition all traffic to V2. So we can just delete the V1 destination altogether and even the wait. And that basically, if we have no wait, it's implicit. It means that 100% of traffic is going to go to this destination. So as soon as we finish editing this resource, all requests should now be going to V2. If I refresh this page, we don't see any requests landing on V1. We see the number of IOPS should increase even further, but it should be able to sustain that load. Everything looks good. You know, these numbers are going up, number of operations per second, but everything's green. So we're happy and we're done with our Canary deployment. Now notice V1 is still deployed, which is, in my opinion, an advantage, right? If for some reason in the next 10 minutes we see an issue with V2, we can again start routing traffic back to V1. So not only do we decouple the deployment of a new app from when it starts receiving traffic, but we have complete control here, which is wonderful. You know, in many systems before Istio, you'd never had that sort of level of granularity. You know, oftentimes with Kubernetes alone, it's the ratio of number of containers you have going. So you're playing with, like, you know, you have 10 V1 containers and 1 V2 container that gives you a crude ability to do a canary deployment, but not something like this. All right, so that's the lab in a nutshell. I sort of got ahead of myself, but you've got the whole lab in front of you. All the instructions are here. And basically what I just did was an illustration of working through this lab. Hopefully I didn't miss any steps in here. All right, let me check in with everyone. How's everyone doing? Are you still with me? Are you following? Was this a good scenario to sort of illustrate what you can do with Istio? So far, we've actually covered a number of use cases. Let's talk about what we have done, what we haven't done. We've installed Istio, we've deployed an application with Envoy sidecars, right? They're part of our mesh. We've exposed our application through Ingress. We've studied observability. We looked at Kiali, Zipkin, Prometheus, and Grafana, and noticed that we didn't really have to do anything to benefit from all those systems. There really was no configuration, no specific thing that I had to do to any of my applications. And from there, we went and looked at security, and then finally traffic shifting. And now there's much more to all of these topics, but hopefully you have a good, solid understanding now of at least what these things are and how they really enable an enterprise. So what I mean by that is you can have a security team defining your authentication and authorization policies. You can have an operations team monitoring your mesh, for example, and the health of the services in that mesh. You can have your development teams that are sort of deploying new versions of their applications, use traffic management as an effective way of having zero downtime deployments. All of the things that we want are essentially at our disposal, and they can actually be parceled out to different teams that have expertise in different areas. Now, some things we didn't talk about. We can inject failures into requests. We can actually tell Envoy, hey, Envoy, add some latency. Every time you call service B, make it last an inordinate amount of time, just to see, to stress test your system, what would happen in an adverse scenario. So you can literally tell it, return a 500 error 10% of the time when under specific conditions. you can increase the resiliency of your system by actually taking out of your mesh any outliers. So services that are misbehaving that could cause a cascading failure can actually be sort of nipped at the butt, so to speak. You can basically not direct any traffic to them for a certain period of time, for like 5 minutes, until they become healthy again. That's essentially in a nutshell, the notion of a circuit breaker. We haven't talked about the fact that our Envoy sidecars can be customized with WebAssembly logic, which is very powerful. We haven't talked about egress gateways. So there's as much more. The point I'm trying to make is there's much more to Istio than what we can cover in the 3 hours that we have. But hopefully our selection of topics was apropos. There's also sort of multi-cluster deployment models that we haven't talked about. And the fact that you don't have to get all of your services running into Kubernetes before taking advantage of Istio. So if you have a service that for whatever reason has to run on a VM, that's called a VM workload. And you can onboard those VMs onto your mesh, and you can have your services running in Istio, call out to that service, and technically that service is part of the mesh, and vice versa. So you don't have to wait until everything is sort of lifted and shifted onto Kubernetes before taking advantage of this sort of ecosystem. All right, so we've got about 10 minutes left, and I'm probably going to turn it over to Peter. We can summarize, and the other thing I want to do is just let you know that these labs are available even beyond the 3 hours of our workshop. So if you want to spend some time later today or tomorrow and sort of revisit this labs at your own pace, you're more than welcome to do that, or use the time we have remaining, or both.
Yeah, that was awesome, Eitan. Thanks for doing that. As you mentioned, like we only like barely scratched the surface with all the features that Istio has to offer. Like it was a conscious choice to pick these topics because these are the most representative, right, and easy to like get started with. But then once you I do encourage you as well, go through the labs again on your own pace, right? 3 hours is very is not enough time, right? Go through them on your own pace. Think about stuff, right? Also, Istio docs are really good. You can dig into those specifics even more. Also, we have free course on Tetrate Academy, which is a free Istio fundamentals course. It's I think almost like a 4-hour course. That goes a little bit deeper than that we went through here in the workshop. And then if you really want to go even deeper, I guess, we also have the Envoy fundamentals course, which will give you the basics of Envoy. So Envoy, as you've learned, is the basic building block of the mesh. So we have that workshop as well. Now, if you want to take everything to the next level even further, we also have Istio certified administrator exam that we do at Tetrate, and this is on par with the any Kubernetes, the CKA and CKAD certifications, but this one is specifically for Istio. Also, if you join the Slack, if you're on the Slack, feel free to ask questions at any time. We are pretty much in that Slack channel every day, more or less. So yeah, I don't have anything else unless anyone else has any questions or anything we can answer additionally. I haven't seen any more questions.
Cool. Yeah, I see. Thanks a lot. Nice add-on session. Yeah, you're very welcome. Yeah, it's our pleasure.
Yeah.
Good. So we want to hear from you. That Slack session is long living. So yeah, Slack channel, sorry, I should say. So that means that if you have a question that pops in your mind, even a week from now, just go ahead and ask it, and we can build a community around this. That'd be great.
All right. Well, thanks everyone, and I hope we see each other next time on a different or the same training. You never know.
Yep. Bye, guys.
Bye.